Hello and welcome back to the very first project on this playlist, that is a playlist on deep learning projects, where we'll be building a bunch of projects on deep learning. And today, the first project as a part of this playlist is Pneumonia project, where we will be designing our neural network and we'll be training our neural network based on certain chest ray images. So without further ado, let us get started and see what it has in store for us. All right, so I'm excited to walk you through this project that is pneumonia detection using CNN, that is convolutional neural network. And as a first step, I'll like to first showcase step-by-step development of a deep learning-based diagnostic model using some of the chest ray images. This project leverages the power of convolutional neural network or CNNs to help in early and accurate detection of pneumonia, a critical and sometimes fatal lung disease. Now, if you're not already aware, pneumonia is a inflammatory condition of the lung affecting primarily the small air sacs known as the alveoli. Uh, Symptoms typically include some combination of productive or dry cough, chest pain, fever, and also difficulty breathing. The severity of this condition is variable, depends on what is the underlying cause. Pneumonia is usually caused by infection with viruses or bacteria, and less commonly by other microorganisms. Certain maybe certain medications or some conditions such as autoimmune diseases can also cause a pneumonia. Chest ray and blood test may help confirm the diagnosis. The diseases may be classified by where it was acquired, such as maybe it can be community acquired pneumonia or hospital acquired pneumonia or maybe healthcare associated pneumonia. But really, the thing that you have to understand about this is why early detection is so crucial. Because if left untreated, pneumonia can escalate rapidly, particularly in vulnerable population like elderly and infants and those with weakened immune system. Early and accurate detection can drastically improve treatment outcomes and reduce the risk of severe complications or even death. One of the most common diagnosis tool is the chest ray, which provides visual evidence if there is a infection or fluid in the lungs. However, interpreting this X-ray requires expertise, and that is where our deep learning model can assist by acting as a second opinion or a support system for radiologists. Now, the normal chest ray is something that looks like one on the left. It depicts clear lungs without any areas of abnormal opacification in the image. And what I mean by that is it shows healthy lung with no cloudy or unusual white spots. Uh, Bacterial pneumonia, that is one in the middle image, it usually appears as a thick, dense white area in one specific part of the lung. You can see over here, the upper part of this right lung, I mean, for the patient's right lung. This is like a concentrated patch of infection. But then there is a third one, that is viral pneumonia, which basically looks different here. You can see instead of a single dense spot or a single cloud, there's a lighter, more scattered hazy pattern that spreads across both the lungs. So this happens because infection affects the lung tissue more broadly in case of viral pneumonia. In short, there are three pneumonia, or should I say three images, chest ray images, chest X-ray images that you have to be aware of. One normal one, that is the clear lung. Second, bacterial pneumonia, that is this dense white patch, and the third one is the viral pneumonia that has this kind of wispy, scattered cloudness in the both lungs. Well, let us see what our project is all about now. Well, the objective is really simple, that we want to detect the pneumonia from chest ray images, chest X-ray images using a CNN, which is known for its strong performance in image classification. So we have used a chest X-ray pneumonia dataset from Mendeley, which will be we'll be exploring shortly, but it contains a large number of labeled X-ray images split into categories of normal and pneumonia. Our approach involves training a convolutional neural network to learn the features of these images and classify them correctly. This is a binary classification problem, and our goal is to make the model both accurate and generalizable. Now, this is the link from where we have got our dataset that we'll be exploring shortly. But the dataset that we'll have, as we'll see shortly, it will have three folders, that is training set, validation set, and testing set. And then all this folder, they contain each image category, that is pneumonia and normal. So there are about 5,000 X-ray images in JPG format and two categories, pneumonia and normal. More on that shortly. But one thing that you have to notice, that the class distribution, that is normal and pneumonia, they are obviously imbalanced with more pneumonia images than normal ones, which will be addressing using techniques like data augmentation and careful model tuning. But the image properties are standardized to simplify processing. That is, each image is resized to this size, that is 150 by 150, and it is converted to RGB format, that is red, green, and blue format, allowing to model to handle input more uniformly. Now, what does the CNN architecture look like? We'll build a sequential model starting with convolutional layers to extract special features from the image, and followed by pooling layers to reduce dimensionality and computation. We'll also use batch normalization to stabilize learning, and dropout layers to maybe reduce overfitting by randomly turning off some neurons during training. After flattening the features, the data will be passed through a fully densed layer, and the final layer will use a sigmoid function. Since this is a binary classification problem, I mean, your X-ray, either it will be mnemonic or it will be normal. There's no third classification. So it's a binary classification problem. So we'll be using sigmoid activation function in this case. All the hidden layers will be using ReLU activation for nonlinearity. Now, to improve the robustness of our model, we will implement data augmentation. This includes things like rotating your image, flipping your image, zooming your image, and maybe a combination of them, so that it simulates the real world variance and also prevents overfitting. We train the model using Adam optimizer or maybe RMS optimizer. We'll see that when we get there. It depends on the accuracy that we are getting, but it adapts. That's Adam optimizer, which adapts the learning rate for faster convergence. The loss function we'll be using is binary cross entropy, which is suitable for two class problems, that is binary classification problem. Training work is conducted. We'll see how many epochs that we'd want, but we'll be starting at a lower end, because it depends on the images that we have and all that, because it can take some time. So obviously we'll be using Google Colab's GPU to train our model. And then we'll also use this ReduceLROnPlateau callback, which basically dynamically lowers the learning rate if the model performance plateaus, helping the network escape local minima. Well, that is all for introduction. Let us head over to Google Colab and see how it all gets implemented in Google Colab. Okay, so here I am in my Google Colab. Right away, you can see that I have created in my drive, I've created a folder, pneumonia project. You can do the same. And also I have downloaded this chest X-ray dataset from this website here, data.mendeley.com. And this is where I have taken my dataset. You can see you have this chest X-ray 2017.zip. You can download it from here. After you have downloaded, you can unzip it and put it in your Google Drive after you have created a folder. But if you just open this, you can see it is having this 3 subfolder as I mentioned, that is trend test, training and training set and testing set and validation set. If you open just one of them, you can see that it has now 2 categories, that is pneumonia and normal. So very, organized data set. We don't have to do anything.
So if you just explore one of this folder, maybe if you can go to pneumonia, and if you just see all of them, they are nothing but bunch of images. If you just see it like this, you can see that it is, some images over here, and all of them, they are X-ray images of, people who are having pneumonia, since it is in this folder pneumonia. And so this is the training dataset that we'll be using in our neural network to train our model on. There are a bunch of images. We cannot explore all of them, but this is how it looks like. So same goes for other folders as well. That is, training and testing here. You can just explore them if you want to. Sorry, you can go to validation maybe and go to pneumonia. And you can see there are a bunch of other images as well. Alright, so this is what we have. Let us now go to our this folder, that is Pneumonia project, and I will open this Google Colab.
Alright, so I'll start with right away. I'll start with naming the Google Colab. So Google Colab file, that is project pneumonia, and I'll start with importing some libraries. I'll start importing NumPy as the foundational one. You can say SNP. So it is a library for numerical operations. Then I'll import pandas as well for data processing. So pandas SPD. Then I'll import some visualization library, Matplotlib. Then you can also import Seaborn, that enhances our visualization, making attractive plots such as maybe count plot and box plots and all those things. So Seaborn is also there. Then I'll import the Keras, that is the library for our deep learning framework, and we import it directly for convenience, but we'll also import some modules of it. So I'll say from Keras.models, I'll import sequential, and what this sequential does is it lets us stack layers one by one to build our CNN. So in CNN there will be multiple layers, input layer, bunch of hidden layers, then output layer. So it will stack them, it will put them together, it will glue them together. Then I'll say from Keras dot layers, you can import dense, and I'll also import convolutional 2D. I'll import MaxPool. I'll say flatten, and I'll see how to import them one by one. Flatten, and I'll also import Dropout and normalization. Let me see if all of this is working fine. I hope it should. Okay, I got an error because I've used, I think here, the MaxPool, the X should be lowercase, otherwise it should be fine. Yeah, it's fine. So let me just explain one by one. So what this dense is doing, this dense is for fully connected layer. So basically every neuron in previous layer, it is connected to every neuron in the next layer. So this is for that. And then convolutional 2D is convolutional, and MaxPool 2D is for pooling. Flatten is to flatten out the data. Dropout is to prevent overfitting, and batch normalization is for stabilizing the training. Now, okay, I've just imported normalization. I'll have to import batch normalization here. Batch normalization. All right, now let us import a few more things. I'll say from TensorFlow dot Keras dot preprocessing dot image. I always advise not to press tab here, because you will get an kind of a licensing warning that you are taking some other's code, which may not be true. So I always suggest do not press tab when this IntelliSense of Google Colab kicks in. But this image data generator, what it is doing, that it will help us augment our images. Remember, I discussed this in the slides that we'll have to augment our training data, since it's imbalanced data. So we'll have to augment that. We'll have to maybe zoom it, flip it, horizontal flip, vertical flip, maybe some rotation and all those things. So this can be done using image data generator. And then we'll have from sklearn, scikit-learn, I'll import model selection. I'll import train test split. And lastly, I'll also import CV2 for image processing tasks, like maybe reading and resizing image. So that is computer vision 2. And I'll also import matrix here, because we'll be obviously testing out our model. So I'll say sklearn dot matrix import classification report and confusion matrix. Okay, so I hope this is just one more thing more remaining. I think it is we'll have to import the callbacks, remember. So ReduceLROnPlateau, I'll say from Keras dot callbacks import ReduceLROnPlateau. Okay, so I think these are the potential libraries that we'll be using, but don't take it as an exhaustive list, because there will be much more that we might have to import later on. But for the starter, this looks fine to me. Now let us go into the dataset. That is, let us explore the dataset. Right away, you can see that in our dataset, this was the folder that I discussed. So you can see that I had just X-ray folder, then I had this kind of subfolder. In this subfolder we also have these two folders again. Now using this, we have to kind of get our data one by one, that is get our images one by one. So this is what we'll be doing now. I'll start with giving a heading that this is, so our task here, the thing that I'm trying to do here is to take those images, grab it and convert into our NumPy array. So NumPy array obviously we'll have to convert, because for people who do not know that it takes our model only works on numbers, and so we have to find a way to convert all our images to NumPy array. Let us see how you do that, and let me just fix the spelling here. This is NEU. So I'll be starting with defining two labels. I'll say that I have labels which are pneumonia, and I also have normal. So these are the two labels that I've created in a list. Then we set some image size which all images will be resized to for consistency, and for that I'm going to say image resize is equal to 150, and you will see how it works later on. But for now, let us create this variable image resize as 150. So then I'm going to create a function, and the objective of a function is to it should take a path and loads images from it. Let us see how this works out. So I'll say def get data, and I'll say it is taking some directory from my Google Colab, and I'm creating an empty list so that this is where we'll be storing our image data and labels. So I'll say this is the data that I have, and this is an empty list. Next is I'll loop through each label in this labels here, right? So just make sure that pneumonia and normal is exactly what you have written here. And whatever the name of these folders are, you have to write it as it is. Okay, there should not be lowercase or uppercase or a bunch of uppercase and a bunch of lowercase. That should not happen. It should be as it is here. Now I'll say for label in labels. So for each of the label, so which are the two labels, pneumonia and normal. So for each of the label, I'm going to construct the full path to the folder for the current label, that is that is maybe pneumonia or maybe normal. So I'll say path equal to os dot path dot join, and I want to join it with directory and label. Now don't worry too much about it because it will all make sense when we get there, but this is what we have. All right, maybe let us try to run this. Okay, if this let us put this to this thing over here. I'll say that first I have to mount my Google Drive. So I'll say from google.colab import drive, and this is drive.mount, and yeah, it's the same thing. So you'll have to mount your Google Colab in this manner. So this is what happens when you press the tab. I suggest that you do not press the tab. Since this was just about mounting the drive, I pressed it and I got this kind of a licensing warning that it is subject to some license. Well, we can ignore this, but I highly recommend again that you do not press the tab here. But for now, let us say since I have mounted my drive, now what I can do is get the path of my folder. Maybe I'll say that in this drive, you can see in my drive, I'll have this pneumonia project, and in pneumonia you can go to Chest X-ray, and here is the from where you can get the copy path, right? So click on copy path here by clicking on this three dots. Click on this and you'll have this option, copy path. So if you copy this, come back here and just press Control V or Command V if you're on Mac, and here you'll have to put that in single quote, and this is the directory that you're going to put in this get data. So let us do that. I'll put this get data over here, get data, and it is taking this directory. Now once it takes this directory, then it is going to should give me this path here, right? If you run this, okay, OS is not defined. Apparently we have not imported OS. That is correct. So let us import that import OS. Yeah, run everything. at the end you just put a print path, and then if you just put those the directory that we grabbed, if you made it pass through get data, right, and run that. Okay, I'll have to remove this get data here, not required. Yeah, so if you run this, you can see this is giving me this normal. So this this entire thing, it is being assigned to this variable called as path. Next is I would like to get the class number from this. For example, I will say that pneumonia is class 0 and normal is class 1 for this. So I'll just remove this because it's not required for us. So I'll just say here the class number, whatever the class that you have, I'm going to assign some number to this. So I'll say labels dot index and then label. Right, so what this is doing, it is going to assign 0 for pneumonia and 1 for normal using this index of the label. Right, again what it is doing, it is taking this pneumonia from here, and this index is pneumonia, index is 0 for pneumonia and 1 for normal. Next is we loop through each images in the labels folder. For that, I'll say that for each of the image in os dot list directory and path, and then you will say that try if. So try block handles any error during image loading, like maybe corrupt files and all that. So we'll it takes care of that, but I'm basically saying I want to check the file should end with .jpg to ensure that we are only processing the jpg image. So thereby I'm just saying that whatever the image that you're getting, it should ends with jpeg. Then we check if the file ends with if you have checked the file does end with jpeg, what we want to do is using CV2 we read the image in grayscale mode and reduce it to one scale, that is black or white instead of RGB. So for that, what I'm going to do is say CV2 dot imread, and I'll say os dot path dot join. Then you take the path comma image, and you want to make sure that you are reading that in grayscale, thereby you just have one channel, because grayscale our just images are just grayscale, right? It's black and white or anywhere between black and white. So this is what it is doing. It is we read the image in grayscale mode, and I'm going to assign it to some variable. I'll call this as let us say image underscore array. But we are not done. We have to make sure that this image that we have created, it should be of optimum size, right? So for that I have to make sure that I resize this. I will say that CV2 dot resize, it takes in the image that it has image underscore arr, then it is taking 150 by 150 that has been assigned to image resize. So I'll take that image resize comma image resize, and this we have to assign to some variable. I'll call this as resized array. Resized array is this. Great. Next is we append the list that we have. So whatever array that we have created, which I have read, and we have resized it to 150 by 150, I want to put that in this list over here. So I'll say data dot append with two things. One is resized array, comma, class number. And then I'm going to say that this is so this is for try, but if we get some error, what we have to do, right? So if error occurs, we'll catch it and print it, then move on to the next images. As simple as that. So it is completely optional, but I'll say exception as E, you print it E. Lastly, we convert the data that we got, which is in a list, right? So we want to convert that to numpy array. So we'll do that, and we'll say, okay, we have run this. Let us try to see what the list is all about, then we'll move forward. So if I just pass this over here, and will take some time to run. There we go. So, oh, I think there's some issue. Let me see. CV2 has no attribute grayscale. Yeah, because this is I am read, don't I am read. All right. We'll do it. We'll do this all together. Let us first get the array. We'll put that in the return here, and that return, it should have indentation with for loop. If this is correct, this is with for loop over here. Yeah, return np.array data, comma, the data type is object. Now why we are using object as data type is object, because it contains both arrays and integers. Let us run this and try to run this as well. Okay, so you can see here that it is now producing all these arrays here. So every individual array that you're getting, it is actually a image that we have transformed into array, right? So this is what we have. Now obviously this is the training data set that we have, but we also have testing and validation sets as well. So I'm going to assign this to train as my variable, and this is training set. So similarly we also have testing set. Yeah, is the same thing. I'll just copy this as it is. Again, do not press tab, not recommended at all. So you have training, and I'll just put that as test, and validation set is the same thing over here. Just one difference, instead of train you have validation. And run this. So obviously it's going to take some time. You have to be patient enough, and because we are dealing with images, and it's always going to take time. So just be aware of that. And one thing is, I just noticed that we are working on CPU. So what I'll do is I'll just stop this, and I'll turn the GPU on and then run all the cells, right? So that it takes lesser time, because otherwise it's going to take forever. So I'll just turn on the GPU like this, and I'll run all the cells. Okay, so it has taken quite some time to actually load all the dataset, but now it is done. And next up is to actually do some data visualization to make sure that everything is intact. So I'll do that. I'll say that this is data visualization and pre-processing. So we have to visualize our data to understand how it looks like. And what I'm going to do is try to get an idea of whether my data set is actually imbalanced, because it is quite normal that people who is going to do the X-ray of themselves, they are suspicious of the fact that they are having pneumonia. So when they're suspicious, the chances of having a pneumonia is always going to be much more than people who are not having pneumonia. So if you're not having symptoms, why would you go to have your X-ray done? So it's expected that the data set that we are collecting, it is going to be always imbalanced, but let us verify that claim and see how much it is imbalanced. So I'll say I'm creating an empty list, and the reason I'm creating this empty list here is because I'll be storing the label names for each training sample. So I'll say this is L is equal to empty list, and then I'm saying for every image in my training data, I would like to take that image, okay, and say that if the image at index 1 is 0, and 0 means we are essentially saying, if you remember, 0 means it is pneumonia, it is having a pneumonia, thereby we have just assigned that 0, the class number is 0. So index is 0. If it is pneumonia, then I'll have to take my list and append it with pneumonia. Next up is to say that it is normal, it is not having any pneumonia. So I'll just say that this is L dot append normal. So this is the list that I've created. This is just having the label names. Then I'll just say at the end that I'll have SNS dot count plot and with L. This will tell me that how many times pneumonia occurs and how many times the normal occurs. Let's run that. Okay, I've got an error that says it should be a boolean value. Let me check that. So yeah, this is not I, this is 1, index 1. There you go. Well, still some issue here. Let me check that again. So this is having, okay, so the problem that we had here is this return key. It should be over here. Be aware of, be absolutely careful about the indentation, otherwise it can give you error. Let us now try this one more time. I'll run this. No need to mount the drive. We will have to load our dataset again, because that goes through this function over here. Okay, so we have loaded our model, and if you just run this cell one more time, you can say that you have pneumonia and normal, that is the two categories of the chest X-ray. You can clearly see that the data set here is very imbalanced. So to increase the number of training example, what we'll have to do is to use data augmentation later on. Now, before moving forward, let us try to preview the images of both the classes, maybe a few of them, just one or two. So you're gonna say plt.figure, fixed size. I'll mention some fixed size as maybe 6x6, and then I'll say that plt.imshow, then train, and I'm going to grab the first figure and the first class, and I'll say CMap as grayscale. Next is to say plt.title and pass in the labels as train, and then 0, then maybe 1 over here. If we just run that, you will see that I'm getting this kind of image, that is it is a X-ray of a pneumonia patient. You can see over here, and I'll say that maybe this is maybe you can display some more image here. Maybe you can take copy of this, and here this is I'll put the training as -1, 0, and here as well this will be -1. So I'm taking the last image here. You can see that this is the normal X-ray that we have. There it is. You can put some more numbers if you want. Maybe you can put -11, and here it would be -11 as well. You can try that as well. You can see you can put any number, and you can just have a look at some of the X-ray images of the chest. Well, so this is about loading of our data. Now what we have to do is we have to create the list of the two that is, you know, the training set and testing set. We have to split that and that. So what I'll do is I will say that I'll create a bunch of empty list. First of all, I will say that I have X-train has this empty list, and Y-train has this empty list here as well, and same for X validation and X testing as well. So X validation, Y validation, then X test, and Y test. Then I'm gonna say that for every feature and label in train, because you know, remember training has two parts, that is your feature and labels. So I'll take my X train, that is a training set, and append it with features. So this is feature training set, and then same goes for training dot append and label. So we have in training set we have the feature set and the test label set. Now we are going to do the same thing for validation as well. Validation dot append feature, and we have to do this for loop in feature comma label in validation, and here as well this is Y validation dot append label. Feature comma label and test turn append, then feature, and then you'll have same for Y test dot append label. Alright, so we have just created this bunch of list. So this is the list of individual features and labels in training set, validation set, and testing set. Now what you have to do is we have to perform a grayscale normalization to reduce the effect of illumination difference, because we need to pre-process them to ensure that they are in the right format, and to enhance the model's ability to learn, we will just put all of them in the same scale. Each image is resized to 150 by 150 pixels and converted to grayscale. But for a CNN to work, it is beneficial to normalize those pixel value. So if you just take a look at our X-train for now, if I say X-train, I'll just remove that. If you look at this X-train and try to run this, you will see that this will actually, if I just put small case x, you can see that it is just bunch of pixel values which is ranging from 0 to 255. You can check that if you want to by grabbing individual arrays, but so this is how it works out. Now what we have to do is to normalize the data, right? So what I'll do is I'll just take this X-train normalize the data. I'll say that take this xtrain, convert into array and divide it by 255. That is the largest pixel value. I'm going to do the same thing for X validation and X test as well. Then this is X test is equal to np.array, then X test divided by 255. Okay, so now since our images are grayscale, they have a single channel, but our CNN in Keras is expected a channel dimension. So we'll reshape our arrays to include those. So I'll resize the data for deep learning, and the way we are going to do that is I'm going to say xtrain dot reshape. It goes from -1 comma image size, image resize rather, comma image resize, because this is the order that it is going to accept the model, and resize comma 1, image resize, and I'm going to assign it to xtrain. This is xtrain. So this when we put that in xtrain, it is going to reshape it into this dimension over here. Okay, now this is ready for CNN. So this is xtrain. I'll do the same thing for ytrain as well. I'll say this is np train. Since it is just going to be it is going to be just an array, I'll just have to convert that into one dimensional array, ytrain, and same thing for X validation as well. Now there you go. So you have your xtrain, ytrain, X validation, Y validation, X test, and Y test ready for you. So now what you have to do is we have to augment our data. Now remember that in our analysis we have already seen that it's an imbalanced data set. So we have to make sure that we expand our data set artificially. We can make our existing dataset even larger. The idea is to alter the training data with small transformations to reproduce the variations. Approaches that alter the training data in ways that change the array representation while keeping the label the same are known as the data augmentation technique. Some popular augmentation people use are grayscales, horizontal flips, vertical flips, random crops, colors, jitters, translations, rotations, and much more. So these are just couple of transformation that I remember, but that can be many more, but we'll use some of them. Let us see. So I'm going to say that image data generator. You can see here, if you do a shift tab, you can see bunch of rotations here. We'll be using some of them. we'll be using feature by center being false, and rotation and all that. So we'll be using bunch of them, but not all of them. I'm going to right away, I'm going to assign it to some variable. I'll say this is the data generator that I have. Okay, so then I'll say that this image generator, it is expecting the feature was underscore center. Well, never mind. Copy this and try to put that in some code over here. Now you can delete this. So we have feature by center as false. So what this is doing, it is set the input mean to 0 over the dataset. Sample by center, it is setting the center of each of the sample at the 0 as well. Then you have some of the things that is feature standard normalization as false. This is divide to divide the inputs by standard deviation of the dataset, and then sample wise standard normalization is dividing each input by its standard deviation. Then you have the rotation. So rotation here is, I'm just saying, so rotation is, I'm putting that as 30. It is in degree, by the way. So I'm basically rotating the images in the degree from you can take any degree from 0 to 180, but I'm rotating with a degree of 30. And then you also have I think width shift underscore and range is equal to 0.1. Then you have the height shift range as well, and I'm also putting that as 0.1. Then you have whether you want to zoom the image, so I'll put the zoom range as 0.2. Yes, then we have horizontal and vertical flip that you can do. So I'm putting horizontal flip as true, but vertical flip as false. So I'll say normal, not normal, horizontal, not the, so vertical flip, it should be false here. All right. And lastly, I'm going to take, so this the instance that I've created, I'll have to fit this instance to my training set. This should be underscore small case x. There you go. All right, so we have what I've done, just to be clear here, I have randomly rotated the training images by 30 degrees, randomly zoomed my images by about 20% on some of the training images. Then I have randomly shifted images horizontally by 10%, and I have randomly shifted images vertically by 10%, by the way 10% of the height. And so then we have flipped the images horizontally. Once so this is done, it will, I think it will significantly augment our our training data set. Next is to create the model. So I'll put a new heading here that is going to be training the model. So I'll start with creating the instance that is model as sequential, and then I'm going to take this instance and add some of the layers. So convolutional 2D, and I'm starting with 32 comma this is a convolution 2D layer with 32 filter, and each of the size, the kernel size, is going to be a 3x3 kernel. And I'm going to say I also want the strides as well, strides as 1, and padding, you can put padding as same, and ReLU, sorry, activation function rather, activation is relu. Then input shape is input_shape is 150 by 150 by 1. Alright, so the thing that we are doing here essentially is the first layer is convolution 2D layer with 32 filters, each of the size 3 by 3, and we called ReLU function for nonlinearity. Next is to get the batch normalization that helps stabilize and speed up the training by normalizing the output. So I'll say model dot add batch normalization. Right, and I'll keep on doing this for a while. I'll once you have normalized this, I'm going to now use MaxPooling to reduce the spatial dimension, keeping the most important features. So I'll say model dot add, and then I'll put MaxPool 2D. It is going to be of 2 by 2 size, and then you have strides as well, strides as 2, and padding would be same as well. Okay, next is to add another convolution 2D layer, but this time with 62 filter to learn more complex pattern. So in this case, what I'll do is I'll just try to take this, copy and paste here, and here this is going to be strides is 1 and padding would be same, but this is going to be 64. There's the only difference between the layer earlier, so this is 64. Okay, so this is what we have in case of model. Next is to add the dropout. To basically what this does is dropout is going to randomly deactivate 10% or whatever the percent that you're choosing. This is 10%, that is I said 10%, so 10% of the neuron to prevent overfitting. So I'll say model dot add dropout and 0.1. okay, so this is there. Now go ahead and do the batch normalization one more time. So in every layer, if you want, you can add a batch normalization, right? So this is batch normalization. Then you can add a MaxPool of 2 by 2 in this case. And so, well, you got this license again, licensing caution. So I'll copy this, create a new code cell here. And there we go. So MaxPool is same. Next is to so this is over here. Next up is to get the convolutional layer 2D one more time and to build a layer of 64. So I'll just copy this, some of the things here, and then I'll change it, right, so that we do not have to type it again and again. So I'll copy this and paste here. And this is having a layer of 64 and stride is 1, padding is same, activation is ReLU. Batch normalization, we don't have to use that. You can avoid dropout and you can put batch normalization here, and then MaxPool 2D, and then you have this 2 by 2, strides is 2, padding is same. Now I'm going to do a paste one more time, but in this case I'm putting the convolutional 2D layer of 128 neuron, right? So 128 neuron, and this is going to be, I think, quite a complex one, so this should run fine. But dropout, and now I'm putting that as 0.2, and then there will be batch normalization. MaxPooling 2D would be 2 by 2, that is fine. So we'll keep everything same here. Then I'll do a copy paste one more time, but this time the neuron is not 128 but 256. So 256 neuron, 3 by 3 filter, strides is 1, padding is same, activation function relu. Dropout is, I'll put 0.2 in this case, and batch normalization is nothing. Then max pooling 2 by 2, strides is 2, padding is same. Finally, this the output layer that we have, but we cannot just take output layer like this. We have to flatten it out. So I'll say that model dot flatten is going to flatten out in 1 dimension vector, and then I'm going to add the dense layer with 128 unit that processes the flattened feature. So I'll say model dot add dense units as 128, then activation as relu. Right, so then it is it's going to add dropout one more time. Dropout 0.2. Then model dot add dense is going to have units as 1, and activation function is going to be sigmoid, since it is a binary class problem that we have. But this is not done because we will have to compile our model. I hope everything that I've written is going to fine. Yeah, so we can compile this. You can use Adam optimizer, or you can use RMS prop as well if you want. So we'll be using, well, let us use Adam only. Compile optimizer is equal to Adam. Then the loss that I have is binary cross entropy, and metric is accuracy. Just one metric here. There we go. So we can also use again RMS prop, which basically adapts the learning rate during training, since it's a binary classification problem. So we can also and we are using binary cross entropy, we can use RMS prop as well. But for now I'm just keeping this to Adam, and I'll keep in fact I'll advise you to just go back and maybe run RMS prop as a optimizer and instead of Adam. But let us take this and get the model summary. I hope I've done most of things right here. Okay, there's a error right away. Let me fix that. So it is having one extra parenthesis. Nope. Yeah, this input shape equal to, that is the issue. This has to be, this D has to be in capital D, and you'll have to fix that everywhere actually. So this is also MaxPool 2D. I didn't notice for some reason, and this has to be 2D as well. So everything you find, everywhere you find this MaxPool 2D, you'll have to do that. Okay, so this is MaxPool 2D over here as well. This is what you have to do. I hope, yeah, here as well it is MaxPool 2D. Just make sure it is doing that. Then here this is convolution 2D, and that is taking 64, 3 by 3, strides is 1, padding is same, and activation function is relu, and you will have to add one more parenthesis here, and same goes, so maybe here and here as well. So just fix this everywhere, because and in flatten as well you'll have one more parenthesis. There you go. Now it should work. So this is optimizer. Unfortunately you have optimizer here. There you go. So this is the model that we have designed basically, but we have not trained it still, right? So next up is we have to train it. All right, so I'll say that here this is we'll first use the training data and validate it with validation set. So we have to set up a callback to reduce the learning rate if validation accuracy kind of flattens out, or the it as you call it plateaus in technical term. So let us do that. I'll try to here I'll say that I want reduce learning rate on plateau, and it is expecting me bunch of things. So monitor is the not validation loss but accuracy. So it depends on the accuracy. As soon as it flattens out, it's going to kind of reduce the learning rate. Then I'm saying patience is equal to, don't worry, I'll explain in a bit what all this means. Then I'm saying verbose is equal to 1 and factor as 0.3. then minimum learning rate, so you cannot go beyond this one, that is maybe 0.0000 and 0.1, and I'm going to assign this to some variable. Let us call this as learning rate reduction. Alright, so what we are doing here is this is just calling the learning rate, and this setting a learning rate scheduler called ReduceLROnPlateau. It is commonly used during model training in libraries like Keras or TensorFlow. Its job is, if the model's performance stops improving, it will reduce the learning rate automatically. That is what its job is. Then I'm saying monitor is equal to validation accuracy. It watches the validation accuracy during training. If the validation accuracy stops improving, the scheduler will react. Patience is basically if the validation accuracy does not improve for 2 consecutive epochs, it will trigger the learning rate reduction. Verbose is it will print the messages to let you know the learning rate has been reduced. Then you have the factor. When triggered, the learning rate will be multiplied by 0.3. That is made 70% smaller. For example, if the learning rate is 0.001, after reduction it becomes 0.001 into whatever the percent that you have, maybe into 0.3%. And then you have the minimum learning rate. So learning rate will not go beyond this one here, to prevent it basically to become quite tiny. What this is doing, the scheduler is, it is helping you to model train better and avoid getting stuck by lowering the learning rate if the validation accuracy is not improving. Now comes the fitting of the data, and this is where it's going to take some time, because it this is the way it works, right? So I'll say that model dot fit, and right away assign it to some variable. Let us call this as a history, and model dot fit, it's having bunch of things. One is xtrain and ytrain. This is the training set that is going to train itself on. Then the batch size is, well, let us not do that. Batch size is 32. Epochs is, I want to put that 12 and not 10, right? So epochs is 12. Validation data is coming from but we have to make sure that this passes through the data gen as well. Data gen dot flow. All right, so it goes through that and then comes to this. Then callbacks, it is going to come from the learning rate. Let me put that in the new line altogether, so that becomes rather easy for you to visualize. So this is validation set, and then you have the callbacks here. So callbacks is learning rate reduction with this kind of a list. There you go. And the okay, run this. Alright, so there's a problem here. Let me check this. And if we check the X-well here, we are reshaping it, and that is going from minus, yeah, that is the issue. So we have to put minus comma 1 here. Alright, then run this, and then you will have to come back to the model that you have created and run this. Alright, so could not interpret binary cross entropy. Let me check that one more time. Maybe there's some issue. So this is BCE as we call it. This is binary underscore cross entropy. That is the issue. You can fix this as well. And then run this. Now it's going to take some time. Still, I've just taken 12 epochs. You can go up to maybe, in fact, I'll go up to 15 epochs. That will be useful. Since we are training this, should train it at the optimum level. So not 12 epochs, but 18 epochs, let us say. Okay, it's going to take some time. Alright, so our model is now trained. Let me just go back and explain you what we have done. So we have taken this model and fit to our X-train and Y-train. So the data gen here that we are using, it is created to something like basically augment our dataset, and then it will slightly modify, rotate, zoom, flip and all that. It will feed batches of 32 samples at a time to model, and this improves generalization and prevents overfitting because model sees slightly different images each time. And then we have the epochs. So you are training the model for 18 full passes over training data. And then you have the validation data. Validation data is you are passing a generator that produces the validation data. For typically for validation, augmentation is not needed. You don't have to augment it. But we are using this data gen still, so that's completely fine. But then we have the callbacks. So this is learning rate and learning rate reduction that we had created in the previous cell over here. So it reduces the learning rate automatically when the validation performance stops improving. So it helps model to converge better in later stages of training. Now, so we have trained our model, but let us see how it has performed. Right, so let us go to our next cell. We'll say that I want to print two things, f literal. We'll say loss of the model is, then model dot evaluate x test comma y test, and then this will give me the two things 0. If you just run this as it is outside of this print statement, if I just do that over here, you can see that it's getting two things. One is accuracy and another one is the loss. So what I'm looking for is the one at I think first is accuracy it is giving me, if it is correct, right? So this is 92% is the accuracy. That's quite good actually. So loss is at 1 and this is 0, and the accuracy of the model is, you'll have to print it again. or you can just display it as it is as well. There's no issue. I'm just trying to be formal here, but you can just run this in this manner, model.evaluate it. It's going to work for you, right? So accuracy of the model is the same thing, model.evaluate. Then you can say this is X test comma Y test here, and you can just put this as 1, and if you want to display this into percent, you can do that as well. So here you can say that this is into 100, and you can say this is now percent. There you go. Alright, so this is this is the loss maybe that we have. This is the accuracy, right? So you can put this like this. 0 is loss. Alright, so this is the model that we are getting now. As I explained earlier, my intuition is that you should be getting a better result if you use RMS prop. So you should definitely do this. You should use the optimizer as RMS prop instead of Adam, and just check your accuracy one more time. But my intuition is again that it should perform much better. It should give you accuracy of around 80%. Now let us try to analyze our model. Analyze. So I'll say that for epochs, and it is going from I to in range from 18. So there are 18 epochs, and I'm creating figure and axis, and say plt dot subplots 1, 2. Then we'll say training accuracy is equal to history dot history accuracy, and it is giving me accuracy over here. And then you'll say training loss is the same thing, history dot history loss, and then validation accuracy is the same thing. I'll just copy this, some of the things here, not actually required to write it. So this is validation accuracy, this is validation loss, and this is validation loss as well. There. Okay, so we have got this. Then I'll say that figure, and then set size inches 20 by 10, x0. We'll say plot epochs. First you are going to say training accuracy, right? And that is going to be geo dash label is training accuracy. Next is to do the same for validation accuracy, right? So you can, most of the things would be same, so you can copy this, paste over here, and this is going to be the validation accuracy, and here as well you can put val accuracy. I'm going to set this title, so x0 dot set underscore title, then training and validation accuracy. Right, so this is the first plot that we have created. Let us check the other ones. That is, I'll see that AX1 on the second plot that we have. So we have two plots, right? Subplots 1 and 2. So on second plot, I'm going to plot the same thing, but just few difference would be there. So this is, I'll copy this as it is and put it over here. Some of the difference would be to not get the accuracy but the losses, and here as well this is going to be a loss, and this also is loss, and this is also loss. This loss. All right, so here as well you'll have to fix this x1 and run this. Okay, so we have fig and not fix. There it is. So this is the plot that we're getting. Let me fix some of the things here. It is not looking at all good, so I'll fix this as not green but a red color, and here as well this is maybe I'll put green dash O and not green O dash, and this is going to be R dash O. Alright, so that way we can get it right. And I'll also put in some legends here. I'll say x0 dot legend is, I have to turn it on, and on x0 dot set x label, this is epochs, x0 dot set y label, it is accuracy. Alright, then copy this, and here you'll have to put that as 1 and 1 here. This is no longer in accuracy, but the y label here is now loss, and rest of things it should remain the same. I'll just put a plt dot show as the last thing. There you go. So this is the plot that we are getting. Right, so you can see here that it is doing quite well. In fact, for 18% I'm getting a accuracy that is quite a at a high level. Training accuracy it is going up to 90%, and here as well in our losses are, it has really going down as we are increasing as we're going towards the 18th epoch. But one more thing that you have to understand, that maybe the change is not that much once you have kind of gone beyond epoch 12. Yes, there's not much of the difference. But so this is the accuracy. Whatever the accuracy, I've accepted the model, but you can go back and change some of the things, maybe try to add many more layers, or try to add some other optimizer to increase the accuracy. But this is the accuracy that I'm getting, and I'm for the timing I'm saying that it is fine for me. So I've accepted my model, and said that this is what I have. But let us try to get the prediction, so that when we get the prediction, we can get the see the performance of my model, that how it has performed when passed to the X test. So we remember the performance so far that I've checked, it is based on the validation set. So we are not doing that. We are now going into the prediction of the testing set. So I'll say model dot predict, and I'm going to say predict the X test. Now if you just run this as it is, you will see bunch of predictions here. What these are the probability values. So probability values in favor of one of the classes, right? Whether it is a 0 and 1. The way you are going to make sense of this is this. So I'm only concerned with the values which are above 50% probability, and I want to take that and put that in, pass that as type integer 32, and that is giving me kind of bunch of 0 and 1. So whatever the probability value that I had, if it was below 50%, it was reduced to 1. If it was above 50, then it is we have just put 1 instead of that. So this is the meaning of the probability value that we got. Right, so now we are going to assign it to something. What are these? These are my prediction values. Again, the 0 stands for pneumonia, and 1 stands for the normal chest X-ray. So this is 0 and 1. Now I'm going to say predictions dot reshape, and it is taking 1 comma minus 1, and if you run this as it is again, you will get, this is predictions, predictions, and if you run that, you will see that I will get this kind of 2-dimensional array. Now I'm not interested in, I'm just interested in one of it, so I'll grab the 0th value, and you can see now I'm getting the 1-dimensional array. In this case, you see there's just 1 square bracket, so one dimensional array. So this I'm going to assign this to predictions, and so let us maybe try to see some of it. I'll say predictions is, I want to grab first 15. There you go. So you can see it is all 0 in fact. Okay, great. Now so what you have to do now is try to get to the try to make sense of this. So I'll go into the classification report. So I'll say print, since classification is always going to be a string, so I'll put that in print classification report, and it is going to take 2 things. One is y test, that is the actual labels, that is y test, and then next is the predicted values that I predicted, so that we can compare the 2 things. I'll say target names here, it is pneumonia, this is of class 0, and we also have normal class, which is should I say class 1. Alright, so this is what you are having, and if you just run that, let me see what the what it is giving me. So you can see here that performance, it is for pneumonia, if it is a pneumonia, I'm getting a good enough performance. You can say precision and recall, it is about 70 to 100%, and accuracy 74%. So it is good. So what this is saying, when it is a pneumonia, I'm doing quite well, but in normal, when you're getting a recall of 30% and a F1 score of 46%, what this is telling me is, there are some times when I'm able to classify normal X-rays as mnemonic ones, right? So which is fine. I mean, you can classify a healthy person as as someone who is having pneumonia, but not the other way around. You cannot say, that is far more detrimental. If you are classifying someone who is not fit or who is having pneumonia, and you say that he is fit, and he tomorrow he comes back and with a larger problem than today, so that is quite a dangerous thing. So you should able to catch the pneumonia X-ray far much more than the other way around. You can call normal, you can misclassify normal ones but not the pneumonia one. So this is what it is doing. So it is perfectly fine. My model is doing completely fine. And remember, I have used the I would say Adam optimizer, not the RMS prop, because I think RMS prop will be doing much well. But after maybe I've run the this entire notebook. Once we have done this, maybe I'll run on RMS prop and show you the result as well. But for now, let us go to the confusion matrix, something that I have not displayed so far. So let us do that. Although we got the classification report, it is it is quite good. So we'll do that. So CM equal to confusion matrix, and it is taking y test, comma, predictions. Check your CM here. There you go. Well, quite a I mean amazing confusion metric. Getting 0 over here, so not too inspiring, but maybe try to get some correctly prediction classes, try to visualize them, try to see that what the prediction was and what we got is doing, visually see the results. So let us do over those here. So remember that this, when I'm saying that predictions that I'm getting, right, this is going to be a bunch of 0 and 7 ones. And if I say this, when I'm saying this is equal to y test, all right, and if you run that, you'll get bunch of Boolean values, which is expected. Now what I want is, let us first grab this, right, because it is going to be a 2-dimensional array. You can this is just going to be a bunch of Boolean values. So what I'm going to do is I'm going to say that put this as np dot non-zero. And if you run that, you will have this bunch of values over here, right? So 0 to whatever the values that we are getting, and I'm going to grab the 0th element of that, because there are 2 elements, right? Or should I say, if you just I'll just show you what we have done. So earlier I had this kind of empty thing in tuple, right? So in this tuple I'm just grabbing the only element in this array. So array was of 2 dimension, right? So it had 2 elements. In that I'm grabbing the first element, which is having this kind of list. So let us check that. So there we go, and this is the correct values. So wherever the true was, I just got those index numbers, and similarly I'll have the incorrect ones, but one difference, the predictions are not equal to y test. So here these are incorrect ones. All right, now let us try to plot this, try to visualize some of the correctly predicted classes. Some correctly predicted classes. All right, so I'll say I is equal to 0, and I'll say for C in correct, remember the array that we have created, and I just want to grab maybe first 8 images. All right, and I'll say that subplot this is going to be, maybe I'll put 4,2 plus 1. Then I'll say that plt dot imshow, it is taking x underscore test of that particular C, and I'm reshaping it to 150 by 150 because that is the size that I know of, and color map is the grayscale. Interpolation is none. Then take the title plt.title and this is going to be f literal, then predicted class is curly bracket predictions C, any of this, and lastly you will see I plus I1. Let us try to run this, see what you're getting. Not very good. So the reason for that is this is 150 by 150, and run that. Okay, but I have to fix this. Fix a lot of things here. I'll have to first fix that I have to say plt dot figure fix size is some number. Let us say this is image of 16 by 5, and also I'll just put some plt dot xtix as this empty list and plt dot ytix as empty list as well. Not good again. Well, let us try to do one more time. So it is giving me a reshaped value, but it is doing a it is doing enough of a good job, but maybe what I'll do is I'll put this as 6 by 15 if this can work. Yeah, now this is good. Alright, so there we go. So you have all the correctly classes over here. So actual class is 0 and predicted class is 0. So this person has pneumonia, this also has a pneumonia, and so on and so forth. But what are the incorrectly predicted class, right? So maybe instead of here I'll put I'm going from 10 to 18. So that I can get some normal X-rays as well. Since the quantity of normal X-rays is not much, so it is expected that you are not getting those, but you can just play around with this number here to get different classes here. But let us try to get some of the incorrectly predicted classes. So what I'll do is I'll copy this and come down here and say that this is incorrectly predicted classes, and this one here as well. I'll take this. Just one difference would be there. I'll show you what that is. So this is everything is fine. I think we just have to get the classes. This is Y test and C, and yeah, this is what you have to do. You have to just put incorrect here. All right, and if you run that, there you go. So you can see the predicted class is 0, actual class is 1, predicted class 0, and actual class is. So again, as I said, that you can grab the unhealthy one as a mnemonic one, but not the other way around. You can see that for all of them, I'm saying that that person has having pneumonia. By the way, 0 means pneumonia, but not the other way around. Rarely you'll find that it. So my model is doing quite well, I think. Alright, now as I promised that at the end, what I'll do is I'll try to put this RMS over here, RMS prop, and try to rerun the entire thing. The only difference would be RMS prop. So run all the cells here. Okay, so we have trained our model, and as I can see over here, it is giving me quite a good result. You can see it is giving me an accuracy of 92%, which is brilliant, right? So it is having an accuracy of very good, that is 92% over here. So you can see that RMS prop is doing a quite a good job. So 92% is on, by the way, training data set. For testing it is 73, that is acceptable, right? But so this is how it works out. Again, there are many more things that you can do in this project. For example, adding few more neurons, adding few more maybe tweak some of the things in batch normalization and dropouts and all those things, using some other optimizer or some other activation function. So that is obviously you can do to get the some other result, but this is the best result that I got. All right, so thank you very much. This is it. This is the first project of this playlist, that is deep learning projects. So I have been uploading many more videos on my YouTube channel. I suggest that you check them out. Many more concepts regarding AI. It is I have discussed that, and some other videos as well that is there. Feel free to like this video and subscribe to the channel, and we'll meet in the next video. Thank you.